14 minutes past 8. In a transformer yard, the metal casing gives off that hot dust smell before anyone sees a spark. Inside the control room, relay screens begin to fill with small errors, then timing slips, then warnings that don't belong together. Nothing dramatic yet. The lights are still on. Elevators still move. Water is still climbing the pipes. But the sound has changed. Out by the high voltage equipment, the steady hum turns rough, like a throat clearing under strain. In orbit, one satellite drops silent for a moment. On the ground, navigation drifts. A system built to look solid starts behaving like glass under pressure. This is how a truly extreme solar particle storm would announce itself to the modern world. Not with a fireball in the sky, but with bad data, hot insulation, and machines pushed outside the rules they were designed for. And the most unsettling part is this. Science now has evidence that something far beyond the 1859 Carrington event already happened once. In 2012, physicist Fusa Miyake found a sharp radiocarbon spike in Japanese cedar rings dated to AD 774 to 775, about 1.2%, far beyond any normal solar cycle. A tree ring archive caught what no human instrument was there to measure, and what it implies is much worse than a single blackout. If you like this kind of deep, evidence-based disaster story, subscribe, because the next clue is buried in wood. That cedar result would have been easier to dismiss if it had stayed in one lab, in one country, in one set of rings. But it didn't. The same abrupt signal turned up again in trees from Europe, North America, and Asia. Quiet wood, cut from different climates and different histories, was holding the same chemical scar. Then the case widened even further. In polar ice, researchers found matching jumps in beryllium-10 and chlorine-36. Cold layers, trapped year after year, were echoing what the cedar had already said. And that matters because wood and ice do not fail in the same way. They do not record the world by the same route. When both of them point to the same narrow window, AD 774 to 775, the room for doubt gets very small. This was not a local fire, not weather, not a strange patch of forest chemistry. It was global. It came from beyond Earth. Now the puzzle turns hard. Carbon-14 does not just appear because a year was unusual. It forms when high-energy particles hit the atmosphere. To leave a radiocarbon spike that sharp, the bombardment had to be immense, far outside any normal solar cycle. So the question is no longer whether something happened. The question is what kind of event can hit the whole planet, write itself into cedar and ice, and still be stronger, perhaps vastly stronger, than the 1859 Carrington storm. That comparison changes the scale of the whole story. In space weather history, 1859 is the reference point. Richard Carrington, the English astronomer whose name became attached to that storm, gave the modern world its benchmark for extreme solar violence. It remains the strongest event of the instrumental era, the one people reach for when they want the worst case that was actually seen, tracked, and written down. And yet, this older event appears to stand above it. Estimates put the AD 774 signal at roughly 10 to 20 times the strength of the Carrington storm in energetic particle terms. That is the detail that turns a strange scientific puzzle into something cold and immediate. Because Carrington is already bad enough to frighten modern grid engineers. A storm far beyond that does not sit in the category of rare weather. It moves into a category with almost no lived memory. The scary part is how quietly that truth arrived. No observatory from 774 left instrument logs. No operator heard relays snapping. No satellite went blind because none existed. The evidence waited inside cedar, inside ice, inside chemistry itself, until Fusa Miyake recognized what the signal meant. So now the question sharpens. If this ancient event truly outranked Carrington, what exactly did it do to Earth's atmosphere? And what would the same kind of hit do to a world full of transformers and satellites? The answer begins high above the weather, in air no one can smell and no one can reach. When a burst of very energetic particles slams into the atmosphere, atoms are struck hard enough to change. That is where carbon-14 comes from, a real physical hit. For the signal in AD 774 to 775 to rise that sharply, the bombardment had to be enormous. Quietly, invisibly, the sky itself was being altered. That is why the old cedar matters so much. Fusa Miyake did not just find an odd ring in Japan. She found proof that the atmosphere had been hit with unusual force, and the ice confirmed it. The event left no instrument printout, no telegraph sparks, no operator notes. It left chemistry, a mark in wood, a mark in frozen layers, the kind of evidence that cannot panic in the moment, cannot exaggerate, cannot misremember. And once that clicks into place, the modern danger becomes much easier to picture. A severe solar particle storm does not need to burn cities to become a civilizational problem. It only has to push delicate systems off balance. Timing first, electronics next, then the long metal arteries of the grid begin to feel currents they were never meant to carry. Which means the real horror of 8774 may not be what it did back then, but what the same kind of impact would do now, when the first thing to heat up is not the sky, but a transformer core. That is where the ancient chemistry reaches straight into the modern grid. The danger is not that this event would strike one machine like a hammer. It is that it would leak into the system through distance, through long transmission lines stretched across whole regions. When Earth's magnetic field is disturbed hard enough, those lines can pick up extra current. Engineers have a dry name for it: geomagnetically induced current. The name sounds harmless. The effect is not. Inside a big transformer, normal power moves in a rhythm the machine was built to handle. But when that unwanted current pushes its way in, the core can begin to saturate. The sound changes first. A deep, steady hum turns jagged, louder, almost angry. Then heat builds where it should not. Insulation starts to cook. Oil warms. The air around the housing takes on that sharp, bitter smell of hot varnish and metal under stress. And this is why the old event matters more than its age suggests. If 8774 was even close to the scale now estimated, the first modern casualties would not be dramatic landmarks. They would be giant, anonymous pieces of hardware hidden behind fences. The machines that quietly keep water moving, signals timed, and cities fed with power. The next problem is worse, because a damaged transformer is not something the world can replace quickly. And that delay is where the story stops being about one bad day and starts becoming about a broken season, maybe longer. A high-voltage transformer is not a spare part sitting on a shelf in a warehouse. It is a custom-built machine, huge, heavy, slow to manufacture, slow to move, and central to everything around it. If a Miyake-class event damaged enough of them at once, utilities would not solve the problem with fast repairs and a few replacement crews. They would enter a queue, and that queue is measured in months. The hard number matters here. Replacements take roughly 12 to 24 months. And only a few factories worldwide build these units. That means the bottleneck is not just engineering, it is industrial capacity. Even if every utility knew exactly what had failed, even if every damaged site were accessible, even if no roads were blocked and no ports delayed shipments, the machines themselves would still take time the grid does not have. Now add the rest of the same event. A severe solar particle storm would not politely damage transformers and leave orbit alone. Satellites would be exposed too. Timing services could drift. Communications could go rough. Navigation could lose accuracy right when crews need it most. So the pressure comes from two directions at once. From above, where spacecraft begin to misbehave, and from below, where the grid starts to overheat. And once both layers are hit together, the countdown in that control room gets much shorter. That shorter countdown is what makes the space layer so dangerous. When people hear solar event, they imagine power lines first. But before the grid fully understands what is happening, orbit may already be taking the hit. A severe particle blast can force satellites into error states, scramble electronics, and blur the timing signals that modern systems quietly depend on. No flame, no impact crater, just screens freezing, clocks drifting, and machines that no longer agree on what time it is. That sounds abstract until the consequences stack up. A control network that loses clean timing begins to hesitate. Navigation loses precision. Communications go noisy at the exact moment operators need clarity. On the ground, none of this smells dramatic yet. There is only stale air in a control room, the soft click of alarms appearing one after another, and that deep transformer note outside getting rougher by the minute. Above, the satellites do not explode in some cinematic flash. They simply stop being trustworthy. This is why the old event is so much worse than an old mystery. Richard Carrington gave history one benchmark in 1859. Fusa Miyake pushed the ceiling much higher in 2012, when that ancient signal was recognized for what it was. The AD 774 Miyake event was not just stronger in theory. It points to a class of impact our infrastructure has never actually lived through. And the next layer down is where invisible drift turns into physical damage. That physical damage begins in places most people never see. A major transformer does not fail like a light bulb. It fails from the inside out. First, the magnetic core is pushed out of its normal rhythm. Then the windings heat unevenly. Then insulation, which is supposed to sit there for years without complaint, starts to break down under stress it was never built to take. The smell comes early. Hot oil, warm varnish, that dry electrical odor that says something sealed and expensive is cooking in the dark. Outside the fence, nothing about that scene looks historic. There is no giant flash over the city. There is just a machine the size of a room growling harder than it should, while operators watch readings that don't want to settle. This is what makes a severe event so deceptive. The disaster begins as noise, heat, and disagreement between instruments. And if the old signal from AD 774 represents the scale researchers now think it does, then the damage would not stay neatly confined to one yard or one utility. Long lines connect distant regions for efficiency. That same reach becomes a weakness when currents begin spreading through the network faster than crews can isolate them. So the event moves through civilization almost sideways, through conductors, timing systems, control logic, all the hidden layers that make modern life feel ordinary. Which raises the ugliest question in the story. Even if warning arrives in time, would operators actually dare to shut enough of the system down before it shuts itself down for them? That decision point is more brutal than it sounds. On paper, operators can protect parts of a grid by taking equipment offline before damage spreads. In reality, that means choosing to cut power on purpose, early, and across systems people depend on every hour. If the warning is wrong, the shutdown itself becomes the crisis. If the warning is right and the response is late, the crisis writes itself into steel, oil, and ash. This is where the ancient event becomes a modern pressure test. The AD 774 Miyake event was recorded in chemistry, not in dispatch logs, so no one alive has operational memory of managing something at that scale. Carrington gave one historical reference. This older signal suggests the ceiling is far higher, and a grid under stress does not wait politely while committees talk. Relays trip, load shifts, heat rises. One bad reading forces another. Picture the room from the opening again. The air is dry from cooling fans. Alarm tones overlap. Someone watches one section go dark to save another. Outside, a transformer casing clicks as metal expands under heat. A choice that looks cautious in 1 minute looks reckless in the next, because every protective move changes the shape of the network. And even if the right switches are thrown in time, the storm is still not finished, because after the grid comes the human layer: water, refrigeration, fuel, hospitals. And those systems fail more quietly than power does. Those quieter failures are the ones people feel in their bodies before they understand them on a screen. A blackout is obvious. The room goes dark, fans stop, the familiar electrical hum disappears. But the deeper damage from an event like this keeps moving after that first silence. Water systems depend on pumps. Refrigeration depends on steady power. Fuel distribution depends on electricity, timing, and communications all staying lined up well enough to function. When those layers start slipping together, the problem is no longer one utility having a bad night. It becomes a chain. In one building, the air turns heavy because cooling has failed. In another, a freezer alarm begins to beep into a room already running on backup. Somewhere else, a pump station falls quiet, and the absence of sound becomes the warning. This is the modern shape of a severe solar particle storm. Not one spectacular flash, but ordinary systems going one by one from automatic to fragile, from fragile to manual, from manual to unavailable. And what makes the AD 774 Miyake event so unnerving is that none of this is science fiction layered onto an old mystery. The ancient signal is real. The atmospheric hit was real. The weak point is us, the world we built around uninterrupted power and trusted timing. Which leaves one hard comparison hanging in the air. If people in 774 endured the impact without a grid, what did the same sky do to a world that had almost nothing to break? That comparison is the strangest turn in the whole puzzle. The atmosphere in 774 was hit hard enough to leave a global chemical mark, but the world below it was almost empty of vulnerable circuitry. No synchronized grids, no satellites, no continent-spanning timing networks. The same event that could shove a modern society off balance may have passed over that earlier world with far less visible damage, simply because there was so much less to break. That does not make it gentle. It makes it quiet. The cedar rings and polar ice say the impact was real whether anyone understood it or not. A tree does not care about empires. Ice does not care about memory. They recorded the hit anyway. That is what gives this story its hardest edge. The archive is better than the eyewitnesses, because the archive cannot be impressed, frightened, or confused. And that flips the usual idea of progress on its head. The older world was not safer because the sky was kinder. It was safer because dependence was smaller. Modern life is faster, cleaner, more connected, and far more exposed to a blow like this. The AD 774 Miyake event forces that realization with almost humiliating clarity. So now, the final pieces come together. An ancient atmosphere-wide strike, a modern web of fragile systems, and a warning problem measured not in comfort, but in decision time. Because once the first alarms begin, the real question is how much time there would actually be. That decision time is the piece people always overestimate. From the outside, it feels like a threat that should arrive with plenty of warning. But a severe event does not translate neatly from space into human response. First, there is the atmospheric hit. Then, there is the question of what systems notice it, which systems trust the warning, and which operators are willing to act before the damage is visible. In a tightly connected world, hesitation is not neutral. It is part of the outcome. This is where the old chemistry becomes almost cruel. Fusa Miyake's finding in 2012 was calm, exact, and silent. A sharp mark in cedar. The event itself would be none of those things for us. For us, it would arrive as confusion. One network reports trouble. Another still looks stable. A satellite goes uncertain. A relay trips where it should not. The room fills with alarm tones and heated air, and nobody in that moment gets to think in centuries. They think in seconds, then minutes. That is why the AD 774 Miyake event matters now more than it did then. The evidence says the ceiling is higher than the modern world likes to imagine. The systems say the margin is thinner than the public understands. And once those two facts are put side by side, the opening scene stops sounding hypothetical. It starts sounding like a rehearsal for a question the grid may have to answer very fast. That answer may be smaller than people want, and that is exactly why it is frightening. Not because nobody would see the threat coming at all, but because seeing it and acting on it are two different things. A severe event does not arrive as a clean movie plot with one siren and one obvious switch to pull. It arrives as partial confidence, conflicting signals, stressed equipment, and consequences that get worse whether the call is early or late. The old cedar and the polar ice give us certainty about one thing only. This class of event is real. The rest belongs to the modern system we built around that fact without really absorbing it. Long lines, precise clocks, satellites overhead, hardware with replacement times measured in months, not hours. Once that framework is in place, the ancient strike stops being a remote curiosity and starts looking like a stress test we have not passed. And that is the piece that lingers. Fusa Miyake found the mark in 2012. Richard Carrington gave history its famous comparison point in 1859. Between those two names sits an uncomfortable lesson. Human memory of danger is often much shorter than the danger itself. We remember the event we measured. We forget the larger one that left no instrument panel behind. So when the first signs appear, the rough transformer hum, the drifting clocks, the satellite that goes uncertain, the real question is no longer what this thing was. It is what remains standing by the time everyone agrees what it is. So the puzzle resolves in the least comforting way possible. The old cedar, the polar ice, the carbon-14 jump, the comparison to Carrington, the long replacement time for the biggest machines in the grid, none of these are loose warnings anymore. Together, they describe one clean fact. The AD 774 Miyake event was not a curiosity trapped in a tree ring archive. It was a real atmospheric strike, global in reach, off-Earth in origin, and far larger than the event modern history treats as its upper limit. That is the ending, and also the trap. Because the world that first absorbed that blow had wood, stone, muscle, wind, and daylight. The world waiting for the next one has relay logic, satellites, pumped water, refrigerated medicine, and transformers that can spend months being built and minutes being ruined. The same sky did not become harsher. The floor beneath it became thinner. And that leaves one image behind. Just a fenced yard, not a blazing horizon or some grand cosmic spectacle. A steel tank humming the wrong way, hot oil smell in the air, and a screen inside a control room filling with faults before the room itself understands what it is looking at. Outside, nothing in the weather seems strange. When that first rough note rises again from the transformer core, how much of the clock will already be gone?